Okay, we're going to continue on here, chapter 17. So we talked about electrochemistry, and last time we got into, I think, galvanic cells. And remember, galvanic cells pretty much have some major sort of parts to it. It will have a sort of solid electrode on one side and one on the other. It will have a solution that has the ions floating around that match the electrodes. And it will also have a salt bridge that connects the two. So as we talked about, this part, a lot of times for this diagram here, is the anode part, and the anode part is where oxidation occurs in a galvanic cell. That means it's going to lose electrons. So those electrons usually go out through a wire, provide some type of voltage, could go do some type of work. It will then go to the other side, which is our cathode, and that is where reduction takes place. And essentially what's going to happen in this case is, since these guys are going to lose electrons on the anode side, they will jump from the solid form really into the solution form, if you will, and really make our positive ions will jump into that solution. As those electrons kind of travel to our cathode side, they will combine and basically reduce down some of these guys and basically take those guys out of solution into the solid. Remember, as we talked about, salt bridge performs a really important sort of aspect. It is a some type of salt solution, ionic solution, and for example, the negative ions in that ionic solution will head this way, and the positive ions here in that solution will head in that direction. And that is to, as we talked about, really prevent the buildup of sort of the wrong charge on each side. If you did not have the salt bridge, again, on the anode side, you would get a really big buildup of positive charge, and that's not going to be really good, as the electrons want to obviously get away from that. And they're going to actually be attracted to that side, and they would actually stay on the anode side. You would get no voltage pretty much. You would kind of kill your galvanic cell, really wouldn't work. The other side as well, the cathode side, if you took out the salt bridge, actually would build up a more negative side charge, as those guys basically will take the positive ions out of solution. It's going to leave a lot of the negative ions in solution on the right hand side. That also is going to, if you did that, really prevent those electrons. They're going to like make a U-turn and go, no thank you, that's like too negative over there, and they're going to again go more towards the positive side. So that salt bridge, what it does again is it allows really not to build up sort of the wrong charge. It will keep the galvanic cell running really well, because it will keep really a more positive sort of situation happening on the cathode side, bless you, than the anode side. And that's going to allow those electrons really to be pulled from our anode to our cathode. Again, these electrons can go out and do some type of work, very similar to what happens with a battery. Those electrons go out, they come and power your device. We could calculate the E of the cell, or the cell voltage, by taking the E of the cathode minus the E of the anode. And these are really those SRP values that we talked about, and that's the standard reduction potential values. Those are a table type values, and as the name implies, is a standard reduction potential, which means, again, typically your anode reaction is incorrect as you would find it on that table. You could actually reverse it to make it the anode connection or reaction. Remember that when you look at the SRP table, a couple important things about it. If you're not given any information about how the reaction is taking place, so you're not given an overall reaction, or it's not told you in words, you could take the one that has the more positive SRP value, should be your cathode. And that's will make that side more positive, bring the electrons to it, and make it all kind of work really well. If you are given, though, an overall reaction, or kind of told how the reaction is taking place, you should look at the reaction and figure out what is being oxidized and what is being reduced. And obviously, whatever is being oxidized would be your anode, and whatever is being reduced would be your cathode. Now, we talked about this equation, and the subtracting are the adding version of it. So again, a reminder that the subtraction here in this equation is to pretty much change the sign in the anode for you, so you don't have to remember to do it. So if you use the subtraction here, you want to go to the SRP table, and even though technically you should reverse the anode reaction that you find in there and change the sign, you could leave the sign just as you find it, and this subtraction will change the sign for you. If you choose that you want to change the sign for the anode one, which will always be the one that you would change, then you could change the sign, but then you should actually add the values after you change the sign together and not subtract them. So again, I think we talked about last time, you might want to pick one and stick with it. I personally use this one, so I don't have to worry about changing signs. I just, put it in there and it does it for me. But you can use either one. Also, a couple other things in terms of those reactions, they are reversible in that SRP table. And again, if you do reverse it, you should change the sign. And if you are sort of quoting a sort of E value for a particular half reaction, it should be the right sign for that, the way the reaction is written. So if it's the reduction reaction, you should have the appropriate sign. But if you flip it around and write the oxidation reaction, you should change the sign if you're kind of quoting the value with the equation. The other thing that's important is sometimes, as we know, we do need to multiply the half reactions by a common number to get the electrons to be the same. And this is one thing that is not affected by it. So if you need to multiply a half reaction by a common number, you do not multiply the E value by that number. So you just kind of leave it alone. It stays the same. Towards the end there, we talked about this in sort of our thermodynamics values. Our delta G is equal to minus NF of E of the cell. And this is our Gibbs free energy. And this is our moles of electrons. That is our friend, Mr. Faraday, and his constant, 96,500 joules per volt per mole. And this is obviously what we just talked about above there, cathode minus anode, basically, in this case. So what we talked about, this one was if you have a positive voltage, that's usually really good, because if we put a positive voltage into this equation, F and N are positive numbers, which will always give you a negative delta G, which means that reaction will be spontaneous when you have a positive cell voltage. Opposite is true if you got a negative cell voltage when you put it into this equation. The negative for the cell voltage and the negative in this equation will then turn your delta G into a positive number, which means the reaction is non-spontaneous. So again, the other thing for this equation, as we talked about, is the N value. It is the total number of electrons that have been transferred, say, from your oxidation to your reduction. But again, you don't want to add both half reaction electrons together. So if you had 2 and 1, 2 electrons in the oxidation half reaction, you should have 2 electrons in the reduction half reaction. N would equal 2, not 4. So you don't want to add them together or anything like that. We also saw one that related the equilibrium constant to it, I believe, as well. A little RT/NF natural log of K in this case. And these are all our same sort of characters. That's our 8.314. That's our temperature in Kelvin. That's obviously our moles of electrons. And that's still our Faraday's constant, our 96,500. And obviously that's our equilibrium constant with is obviously products over reactions, just like we normally would calculate it. Again, all three of these things really should probably agree with each other. So for example, again, if you have a large value of K, as we know, that means that when you reach equilibrium, you should mainly have products. And the only way to have products at equilibrium is that reaction probably should be spontaneous with a negative delta G and probably should have some positive voltage to get you there. And vice versa, if you have a small value of K, that means, like we've talked about before, you have mainly reactants at equilibrium, which means the reaction is really not going to product side. It's kind of staying at the reactant side, and it's going to be non-spontaneous, probably should have a positive delta G, and also should probably have a negative E of the cell as well. And that all being pretty much means it's going to stay on the reactant side. Any questions on any of that stuff there? So I think we finished up with the gold example last time, I think. Yeah. Okay. So I think we're on to, not that one, that's the one we did. All right, we're on to this one here, I think. So take a few minutes here, see what you come up with. We're looking for the equilibrium constant here in this following reaction. There's your SRP values given to you. See what you come up with. Okay, let's take a look. So again, these would be the SRP values that you would find from the table. And again, here in this particular case, you would not want to go with the more positive one as your cathode because they actually gave us the reaction. So we do want to look at the reaction, see what's going on. And if we do, we can see that iron's going from +2 to 0. So again, if you did the little number line type thing, we start at +2, end at 0. It's actually going through reduction as it's becoming more negative here. And if you look at the silver, it's going from 0 to +1, which would be there heading in that direction. And it's becoming more positive, which means it's going through oxidation. So in this case, if you just chose the more positive one here as your cathode, you would be incorrect in this case. And by the way, in most problems, this would not be given to you. It just happened to be in this problem. So you do need to make sure that you look at the equation and figure out what's going on to determine it. So that is why in this case, even though iron is not more positive, in the case of the reaction we're looking at, it is actually being reduced and it is our cathode. Any questions on that there? So now that we have this sort of sorted out, that again, this is our cathode, this obviously would be our anode. We want to find the equilibrium constant, so clearly we would want to use the one that had the K value in it, and that should be this equation here. We could calculate our E of the cell by taking our cathode minus our anode. And once again here, I'm going to subtract, so I'm not going to change anybody's sign. If you chose to change the sign, again, you should add instead of subtract at this point. So we will go with the cathode, which again, here is our iron, minus our anode, which is our silver. And in this particular case here, we get a 0.44 on the negative there, and a 0.80, going to give us a negative 1.24 volts. That will be our E of our cell. Our R is our gas constant. Our temperature here, we need to add a 273, so that's going to give us a 298 Kelvin. The N in this case is 2, right? As there are 2 electrons. Again, you do not add them together. And F again is our constant. So at this point, we should have most of what we need. Minus 1.24 volts would equal our gas constant. Again, the 8.314 version of it. Our temperature, which is 298, divided by N, which is 2 moles. And our F, which is 96,500, if we use the rounded number there, and natural log of K. So really to solve this at this point, we're going to basically multiply everything that's on the bottom to the other side. And once we're done with that, I'm going to come back and divide by whatever's on the top. So if I do all that there, I'm going to take negative 1.24 times 2 times 96,500. I'm then going to divide it by 8.314, hit equals, divided by 298, hit equals. That's going to give me a negative 96.595-ish, equals the natural log of K in this case. To get rid of the natural log, we're going to do E of both sides there. And that will give me a K. Here, I'm going to use the entire number on my calculator. So if you did round, you might get a slightly different front number. But the back number should be okay. So without rounding on my calculator, 1.1 times 10 to the minus 42. And as I mentioned, what I'm talking about is if you did round, this number should be the same, but maybe the front number might be slightly different depending on sort of where you rounded. Any questions on that there? Now, does all these numbers agree with each other? So I have a negative 1.24 volts. That means this reaction is spontaneous or non-spontaneous? This reaction should be non-spontaneous because if I put it into my delta G is equal to minus NFE, negative there and negative there turns my delta G into a positive number, which means it's non-spontaneous. So since it's non-spontaneous, that means I probably have mainly reactants, which means my equilibrium constant should be small, and to the minus 42 would qualify as small, I would say, yeah. So again, these are things you want to think about as you're doing some of these calculations. All these things should sort of agree with each other. Any questions on that there? All right, let's try another one then, I think, or not. Good conversation. Let's talk about a little bit about what happens in non-standard conditions. So remember, as we've been talking about, to say the thermodynamics chapter and just in general, when we talk about sort of standard conditions, that's usually something with a temperature that's 25 degrees Celsius. If we're talking about concentrations, they should be 1 molar. If we're talking about pressures, they should be 1 atmosphere. And really, when you see these little sort of knots or circles next to these values, that's pretty much what it kind of means. It means under standard conditions. These are typically the conditions that most sort of table values that you look up have been basically found at, 25 degrees, 1 atmosphere, 1 molar. So we saw one in our thermodynamics chapter there with delta G in a non-standard condition. Delta G equals delta G naught plus RT natural log of Q. Kind of tying that together with our delta G here in our E of the cell gives us an equation that we use also for sort of non-standard conditions. And that is what is sometimes referred to as the Nernst equation. And the Nernst equation is E is equal to E naught minus RT NF natural log of Q. If you're at 25 degrees Celsius, you can reduce these down, kind of like what we saw, I think, on the other equation. You could use 0.0257 volts over N, natural log of Q, or if you want the base log 10, 0.0592. Again, you don't necessarily have to worry about these two equations. You could just put all the numbers into this equation and it'll all come out the same, which is the Nernst equation. So that E, without the little circle on top there, or the knot, is sort of under non-standard conditions. So in most cases, a lot of cases, is something like the concentration is not 1 molar, or you have pressures that are not 1 atmosphere. Those are probably going to be most of the time you're going to come across. E naught here is the one that we've been calculating. So that is to the SRP table, taking your cathode minus your anode, just like we've done before. R is our gas constant, still the 8.314 version. T is still our temperature in Kelvin. N is still, again, our moles of electrons. F is Faraday's constant. And Q is our reaction quotient. And we've seen in a number of different places a reminder that we do calculate Q, obviously, the exact same way that we calculate K, which is basically our products over our reactants. Obviously, any coefficients, you got to use those as well. So this is what we would use in a sort of non-standard conditions. And I would say probably in most cases, that's probably where you're going to see the non-standard part come into play, something about pressure, something about concentrations that are not 1. Any questions on that there? All right, now let's try one perhaps. There we go. All right, so here's some SRP values. And will the following reaction occur spontaneously at 25 degrees Celsius if you have an iron 2 concentration of 0.6 and a cadmium of 0.01 following that reaction there? And again, our SRP values there. So see what you come up with here. Okay, let's take a look and see. So once again, these would be our SRP values. Again, this will not always be given to you. Most likely it will not. So once again, here, this is a situation where we do want to go to the equation, make sure everything is all good. So again, that's a +2 and a 0. And our cadmium here is going from 0 to +2. So once again, our iron is being reduced, which means it's our cathode. And it is the cadmium here that is being oxidized. And that would be our anode. Again, if you simply went by the values in the table, you would be wrong if you chose the more positive one. So again, you want to make sure that you do look at the actual equation. In this case, for sure, the little part there about oxidation reduction will not be given to you. Yeah. All right. We are also should recognize that these concentrations here are not 1 molar, which means we're in some non-standard conditions. So again, if it was standard conditions, those guys would all be 1 molar, which they are not. So that tells us we should use the Nernst equation in this case. And that would be our E is equal to our E naught minus our RT/NF natural log of Q. So we do want to calculate the E of the cell under standard conditions, and we would just go to the SRP value here table to do that. So our E naught of our cell is going to be our cathode minus our anode. And once again here, I'm not going to change the sign because I'm subtracting. So our cathode in this case being our iron, which is 0.44 volts, minus our anode, which is minus 0.4 volts. Going to give us an E of the cell here of negative 0.44 minus 0.4. Gets us a minus 0.04 volts. So under standard conditions, is this reaction spontaneous? It is not, right? We got a negative voltage, which again would lead us to a positive delta G, which means we would not be spontaneous here. So here we are playing with the concentration. So we're going to see if maybe by playing with the concentrations in this case, maybe we can make this reaction become spontaneous. So we do have our E of our cell. R is a constant. Temperature, again, is going to be 298 in this case. Looking at our half reactions here, our N value is going to be 2, and Faraday's constant. The other thing that we might need there is Q. So to calculate Q, again, is the products over the reactants. So that is the concentration of cadmium divided by the concentration of iron. And like normal, our solids here are left out. Like we do not put them in there. That's also why you don't have any type of values for those guys. You only have 2 values. So if we put these values in here, we got 0.01 for our cadmium and 0.6 there for our iron. And that gets us, call it 0.016667 here. All right, at this point, I think we got everything we need on the right-hand side of the equation. So our E will equal our minus 0.04 volts minus our 8.314 joules per Kelvin per mole times our 298, which is our temperature converted to Kelvin, divided by our 2 moles, which is our number of electrons, and our 96,500, which is our Faraday's constant, natural log of 0.016667, if you will. All right, I'm going to pretty much kind of clean up everything behind this minus sign here. So I'm going to first take the natural log of my Q. I'm then going to times it by 8.314. I'm also going to times it by 298. I'm going to divide it by 2, hit equals, divided by 96,500 and hit equals. And that is going to give me, after we clean it up here, negative 0.040 volts minus a minus 0.05255997. Not rounding too much there, I suppose. All right, now what's left, obviously, is to subtract those 2 numbers. So I'm going to take negative 0.04. I'll get a minus from my number I got on my calculator. And I didn't round too much, but I ended up with 0.013 volts. We'll do a little bit of rounding at this point here. First off, any questions on the calculation part? Is this reaction spontaneous? It is, barely. We got a little bit of positive voltage, which I guess is better than none. And since that technically is a positive voltage, it technically would give us a negative delta G. Not very much going on, but it is still barely crawled in there, so it would be spontaneous. So here, by changing the concentrations, we were able to sort of make this non-spontaneous reaction kind of become spontaneous. And obviously, in this case, you can play with the concentrations. You can also play with pressures if you're dealing with gases and things of that nature. Yes. Yeah, so there's two ways that you should choose which one is your cathode and anode, and it does depend on the situation. So in a situation where you are not given any overall reaction or anything like that, or told how the reaction is taking place, but you just simply have a question where they're like, hey, you built this galvanic cell of these two things, right? You would go to the SRP table, you would look at the SRP values for each of those guys, and whichever one's more positive should be your cathode, and whichever one obviously is less positive would be your anode. In a situation like what we have in this problem, and even the previous problem, and even the one we did at the end last time, which was the gold example, in all those examples, they basically told us how the reaction is happening or what reaction we're looking at. And in this particular case, they gave us the actual reaction right here. And this is the overall reaction that we're actually looking at in this particular problem. So because they gave us the overall reaction, we do not want to go by the more positive ones to our cathode. We actually want to look at the reaction and see what is being oxidized and what is being reduced. And in this case, if you look at the iron, it's going from +2 to 0, which means it is being reduced. And that would then mean that the iron in this reaction, because that's the one we're looking at, is actually going to be our cathode. And when you look at the cadmium, it's going from 0 to +2, which means it's being oxidized, which means in this case of this reaction, that should be the anode in this case. And that's why we chose it in that direction here. So always default to the overall reaction if they give it to you, or they tell you how it's happening. If they don't give you any of that information, then just roll with the more positive one as your cathode. Yeah. Yeah, so that's basically what the Nernst equation is for. Something that you're doing with, say, this galvanic cell is not under standard conditions. In this case, it's actually the concentrations means that they're not under standard conditions, because under standard conditions, they would have to be 1 molar. So as soon as you see any type of concentration that's not 1 molar, and even if you're doing something with pressures and you don't see a pressure that's 1 atmosphere, then that means it's under non-standard conditions, and that's why you would want to use this equation. Yeah. If it was standard conditions, it would actually just be this guy right here. If you were looking for just what the E of the cell would be, because that's under standard conditions. And that means that's pretty much what you find in most tables that you look up values in tables, they're standard conditions. So, yeah. Other questions? Yeah. By the way, speaking of this equation and one that we used previously that has to do with the equilibrium constant. I'll just do it here. That other equation that involved the equilibrium constant really is sort of derived from the Nernst equation. And that is because if we are at, kind of like what we talked about in thermodynamics, if we are at equilibrium, E would equal 0 and Q would then be the equilibrium constant. So if you did that, that is how we get to that other equation that we used earlier. And that is when we subtract all that to the other side, gives us RT/NF natural log of K is basically equal to our E of naught. So that equation that we use with the equilibrium constant does come from the Nernst equation. And the important part of that is why there is no negative on this guy, but we are subtracting here. So you want to be careful of the sign. People a lot of times with the Nernst equation always wants to add it. And people always want to kind of put a negative on that guy with the equilibrium constant. So just keep that in mind. I think people want to add the Nernst equation because of this one. You know, we kind of add that one. That's delta G and delta G naught. But just keep that in mind of those guys. But that's, if you ever can't remember, perhaps the one with the equilibrium constant, but you do know the Nernst equation, you could kind of get to that guy by basically putting those guys equal to 0. Any questions on that there? All right, then let us try another one here, I think. All right, let's do this one. Forget the balancing part. Let's just calculate E of the cell and the equilibrium constant here. And again, these obviously would be our table SRP values here. Okay, let's take a look. So in this one, we're looking for E and K. So we would probably want to use obviously the version there that had the K value in it, which would be again RT and F natural log of K. We also will do our E of the cell, E of our cathode minus E of our anode. So in this case, we do want to determine which one it is. We do not want to go just solely by the SRP values since we are given the equation. So we want to look at it, and probably the easiest one maybe to look at would be the chromium that starts at +2, ends at +3. So again, if you were sort of following on the number line, +2 to +3, heading in that direction. So it is being oxidized there, our chromium. So since that is being oxidized, that is our anode. By default, that would then make this guy being reduced, which is our cathode. By the way, oxidation state here, -2, that's a 12. And that's a -2 is a 10. That's like a 2.5 right there. That's a -2, which is a 6. And that's like a 2 there. So the sulfur actually going from 2.5 to 2, just a little bit, they're being reduced. But again, as long as you can determine one of them, that's good. So we have that. So we could do our E of our cell, which again here would be our cathode, which we decided was that guy right there. So 0.17 volts minus our chromium, which is our anode, minus 0.5 volts. And again, I'm not going to change the sign since I'm subtracting. And in this case, looks like a 0.67 volts here would be our cell voltage. We now pretty much have everything we need for the top equation. N in this case would equal 2, as we do have 2 there, but only 1 here. So technically, to balance out this equation, we would need to multiply everybody by 2 to get to the proper number of electrons. So putting that in there, that's a 0.67 volts is equal to 8.314, which is our gas constant, Kelvin mole, and our 298 temperature divided by our 2 moles of electrons and our 96,500 joules per volt per mole. And that's going to equal our natural log of K, which is what we're looking for here, I believe. So once again, what I'm going to do is basically multiply what's on the bottom to the other side. And when I'm done, I'm going to take whatever's on top and divide it. And if I do all that to kind of clear up to the other side, I got 0.67 times 2 times 96,500 divided by 8.314 hit equals, divided by 298 hit equals. Gonna give us, I believe here, like a 52.19 equals the natural log of K. At this point, we're going to do E of both sides. And again, I'm just going to take the number that's in my calculator, not the rounded number. So again, if you rounded, you might get a slightly different number there in the front. Looks like without rounding in my calculator, 4.6 times 10 to the 22, perhaps. Yeah. And again, if you round it somewhere along the way, this number might be a little bit different, but that number hopefully should be okay. Yeah. Do you have to reverse the chromium equation? You do in this case. So that's why it's our anode. I didn't put them together to balance them, but that's how you would balance it. Basically, you would, if you did balance it, we would reverse the chromium there, and that would give us this, right? Goes to 2 plus 2 electrons. Then adding to that guy would give us our overall reaction where the electrons would cancel. So really, if we balance it up, I think we should end up with perhaps a 2 there, a 2 there, and like a 2 there. Yes, when it's all added back together. Yeah. But yeah, if you reverse the chromium, you could change the sign and then just add them together, obviously, then rather than subtract. Yeah. Other questions? Again, everything does seem to make sense in terms of their values. We had a positive voltage here, right? Which means The reaction should be spontaneous because that should lead us to a negative delta G if we calculated it. And negative delta G, which means it's spontaneous, means we should have some products. And since we have some products there, we should probably have a large value of K. And again, to the 22 would definitely qualify as a large value of K in this case. Yeah. Any questions on any of those there? Yeah. Yeah, I personally, yeah, you could do that. I personally, math wise, basically took the 0.67. I multiplied by what was on the bottom, which was 2 and 96,500. I then divided by what was on top, which was 8.314 and 298. Yeah. Again, you might not want to put everything in all at once into your calculator. You probably want to use some equal size, especially when you're doing the dividing part. If you didn't combine them first and just get one number to divide. Other questions? Okay, then let us continue on and talk a little bit about galvanic cells, which sort of focuses on batteries, I guess, and how they're very similar and maybe a little bit different as well. So you're not going to be asked to write any specific batteries, half reactions, or anything like that. But you do need to just have an understanding, again, how a battery is similar and maybe how it's a little bit different than a traditional galvanic cell that you would build in a laboratory. Kind of sounds like a test question. All right, so batteries are galvanic cells, or series really of galvanic cells combined, where we use, again, the direct sort of electrical current to do really some type of work. So if you ever looked in your battery compartments, right, there's always some like wire type thing in there, right? And that's kind of where those electrons sort of travel through to the other side. Couple of differences between sort of a traditional galvanic cell, obviously, and a battery is more self-contained. There's really kind of no traditional salt bridge. Hopefully it doesn't leak all over yourself. Trying to put all those beakers into your device would probably not work so well. So it's a nice self-contained sort of galvanic cell. There are certain things that sort of function like a salt bridge and sort of keep things floating around or going, well, I guess not really floating, I suppose. So let's talk about this type of battery, which I'm going to go with a Duracell. Kind of looks like it, maybe. This is sometimes referred to as a dry cell, and basically doesn't have a fluid compartment. It has an anode, which is basically the zinc can or container. It's in contact with a electrolyte and also MnO2. The carbon rod that's sort of in the middle there is our cathode. And again, right, we have a negative side to a battery, right, and a positive side to the battery. Kind of like a traditional galvanic cell, right? The electrons should run away from the negative side, right, through the wire to the positive side, right, of your battery. And that will make it hopefully spontaneous, and the thing will work, right? If you put your battery in backwards, you basically made a non-spontaneous cell, right? And it doesn't work, right? Which is why you have to turn it and flip it the other way. Inside here, we have sort of this paste in here that really sort of functions a little bit like a salt bridge to keep everything sort of flowing in this sort of battery. These type of batteries have a voltage of 1.5 volts, regardless really of the size. So if you have like a D or a C or a AA or a AAA, they all basically have the same voltage. They could just allow this reaction to occur a lot longer, right? Depending on sort of the size of it. So here, if we look at our anode part here in our reaction, it's our zinc going from 0 to +2, again being oxidized in this particular case. And in the case of our Mn here, that is going to be a +4. And over here is a +3, which means it's being reduced in this case. And this is the overall reaction that is taking place. And obviously, this will sort of continue this process. Obviously, at some point, some of this stuff sort of wears out and the composition changes a little bit, so it doesn't become as effective as it was originally. And then you got to go get some new batteries or stuff like that. Another type of battery is a mercury battery, which is a little bit different and a little bit similar as well. Mercury batteries are a lot of times used in medicine, in electronic industry. They have a zinc anode. which is in contact with mercury, which is inside. And it's also in contact inside with a really strong alkaline electrolyte. Alkaline means basic, right? So alkaline, basic. Hence the potassium hydroxide, which would definitely qualify as basic, as that's a strong base. Again, that strong base, strong electrolyte, right, is going to kind of help keep everything flowing in terms of charge and keep the charges sort of working correctly. There's no change in the electrolyte composition during operation, which means pretty much is pretty long lasting because of that. So you're not going degrading your inner part of your battery, maybe like you are with the previous type of battery where it's sort of changed a little bit over time. Now, the overall reaction also involves really only solid material, which is really good for sort of long life and also for like rechargeability in a lot of cases in terms of battery. So if you look at the overall sort of guy, we kind of have solid on both sides. So through sort of recharging and those type of things, this is usually a really good sign for kind of keeping the battery sustainable and going. You get a little less of a voltage there. We got 1.35 volts. And once again, we have our zinc, which is really 0 to +2 here being oxidized, and our mercury +2 to 0 here being reduced in this particular case. Lead storage battery, which is also known as usually the car battery, is really a series of sort of cells that are joined together. Each one gives you basically 2 volts, and there's about 6 of them. And that's your 12-volt battery that you traditionally have in your engine. Although nowadays they don't put them a lot of times in the engine. Sometimes they're in other places in the car. But that is enough to basically sort of power everything up and turn on your car, right, to get everything going, unless you're late for wherever you're going, and then it's going to be dead on you, of course, right? And then you go, I hope it's not the alternator. I hope it's just the battery, right? And we have things like alternators and stuff like that, so we don't drain the battery, right? So it sort of keeps that voltage variable, and we also can recharge it as we're driving, which if you ever had to jump your car, right, they tell you keep it on, drive it for 30 minutes, hope for the best, right, before you shut it off. And you know, you can sort of recharge it and we'll come back to life in a lot of cases. You'll be okay. Good batteries usually have sort of a density there of 1.2 grams per milliliter. And sometimes in cold weather, it affects, you know, batteries, how they work, because all the sort of battery acid and all that, a little bit more viscous. So, you know, it doesn't kind of turn over or flow as well as it maybe should. Here's a cross section of a car battery here. And again, you can see the series of cells, which obviously you can increase your voltage by really lining them up in a series, and you basically just add up all the voltages. We have our anode, right, where our oxidation should occur, our cathode, electrons sort of going across that way. That's also when you get the jumper cables and go, red one goes where, which one, or the black one goes which one. Then you just call AAA and hope for the best, right? And the else jumps you. But here we go. This is 0 and this is +2. And again, that's being oxidized in this particular case. And we have our cathode reaction going on down there. Most of the batteries nowadays are sealed, right? And that's hence we have sulfuric acid in there. And that obviously is a strong electrolyte. Again, that's going to help kind of keep everything flowing and stuff like that as well. This is a lithium battery, and a lithium battery has an anode that has some type of carbon type material like graphite, and has holes in it that allows really the lithium ions to sort of flow to the other side. The cathode in these type of batteries have some type of transition metal that's big enough to kind of hold those ions that are coming across to the other side. The nice thing about this is it can be charged hundreds of times without deterioration. Lithium is also a really light metal, which is why for a lot of years they use lithium batteries for a lot of things like cordless drills, right, phones, and all those things. You could charge it and all those things, and it's, you know, it's able to kind of replenish itself a lot. This is a fuel cell, which is typically not traditionally a sort of battery, but sort of also operates like a battery. And for a lot of years, this is sort of what they wanted to sort of turn cars into, and how they wanted them to function as sort of hydrogen fuel cells. And in this case, we would have a steady stream of oxygen and hydrogen coming in there. And obviously here we have some electrodes, solid versions of those electrodes. We have a really strong potassium hydroxide there, electrolyte solution, again, to kind of keep it all flowing together. And really the reason here they want to do that, obviously, are 0 to +1 here, 0 to -2 coming on there. And the reason they wanted to turn our sort of cars into that, right, is the basic byproduct of it is just water being made, right? So less pollutants and stuff like that. Clearly, we are not a hydrogen economy, and it's a little bit different to sort of put hydrogen gas in than regular sort of gas. So we've obviously now moved more towards hybrids and now really just straight batteries as well in terms of our cars. Any questions on batteries there? All right, we're also going to talk a little bit about corrosion. So same idea. You kind of need to know what corrosion is, and maybe as we'll talk about a couple ways to maybe prevent corrosion. So corrosion is really sort of returning the metals to their natural state. About a long time ago, of iron production was used to basically replace rusted metals. Any metal that basically has an SRP value less positive than oxygen is susceptible to going through corrosion. And that is because we just think about the SRP values and we have oxygen and a metal. And if oxygen is more positive than the metal here, that means oxygen will be our cathode in our galvanic cell. And that means that our metal will be our anode, which means it's going to go through oxidation and obviously will go through corrosion. So any metal that obviously has that less positive SRP value than oxygen is pretty susceptible to going through corrosion and really oxidation, and it's going to be a spontaneous sort of process that's going to allow it to basically occur. Now, not necessarily all oxidation or corrosion of metals is necessarily a bad thing. Sometimes the sort of corrosion can create a layer that will actually protect what's underneath in terms of the metal that hasn't gone through corrosion in that case. So for example, aluminum can do that. Aluminum will make sort of a thin little layer as it goes through oxidation, and it will actually prevent further corrosion to occur from the metals underneath. Iron does the same thing, except the problem is when we do iron, it falls off, which obviously will expose more new metal to go through oxidation. That's rust, basically, right? So when iron starts to rust, it does create a layer, but that layer is pretty brittle and will fall off and expose pretty brand new stuff to go through oxidation. Copper also can be oxidized. It makes that nice greenish patina color that some people really like, right? And it can charge you a lot of money for in some cases. Silver tarnishes, that's silver sulfide. And gold at 1.5 volts is a larger positive SRP value than oxygen, which means it doesn't really go through corrosion. And that is because when we hook up oxygen and gold together, gold is actually more positive than oxygen. And that means when those two get together, it's actually the gold is going to be our cathode, and the oxygen here will be our anode, where oxidation will occur. So gold is pretty much protected in that particular case. Now, as I mentioned before, in terms of rust, you pretty much need a few things to occur to make rust. You need iron, you need some moisture, and you need some oxygen. And a lot of steel has these sort of non-uniform points, kind of divots in it, and that's a good place where moisture could kind of hang out. And obviously there's oxygen in the air. So it's a really good sort of breeding ground for rust to sort of occur. Rust is iron 3 oxide, but it actually occurs in sort of two steps. The iron actually goes to iron 2, and then the iron 2 is actually further oxidized to iron 3, and that's what then will obviously make rust. And as we can see from this picture here, we got those sort of non-uniform points where moisture can sit, and obviously our rust problem again is this will have a tendency to fall off, and now all that brand new sort of metal underneath can continue to go through rust until pretty much you could put your finger through it, right, and break it sometimes. And that usually costs money, as I see here with the dollar sign, I'm imagining. So there are some ways that we could prevent corrosion, some type of application of a coating like paint or metal plating. There's a whole line, right, of Rust-Oleum paints, right? And I imagine from the name, that's probably what it was supposed to do, right? You paint it over and it doesn't rust out, or as most people wait until their metal chair gets rusted and then paint over it, right? Hopefully you sand it a little bit before, I suppose. You could also do some type of plating. They, again, sometimes will form a nice sort of protective layer. For example, zinc galvanizing. Zinc is actually a more active metal than iron. So when we look at zinc and iron, in this case, it is actually the iron that is more positive than the zinc. So when we have zinc and iron, when we do some type of galvanizing, the zinc here is going to be our anode and the iron is going to be our cathode. So pretty much all the bad stuff happens to the coating, the zinc, right? And again, it kind of protects the iron that may be underneath it, sometimes referred to as a sacrificial sort of coating. Again, all the bad stuff sort of happens to it. Alloying is another way that you could prevent sort of corrosion. You could add some other sort of elements in there, and that will sort of change sometimes the metal to more of a positive SRP, kind of like a noble metal, and again, that would prevent some corrosion. Cathodic protection is a system where, for example, you do have sort of a sacrificial sort of guy that's going to do that. So if you ever like buried like a pipeline or a big tank underground, right? Underground has a lot of moisture, right? Which is pretty ripe for it to start to go through corrosion. You could connect something like magnesium to it. And again, in this case, magnesium is a better reducing agent than iron. Reducing agents are things that get oxidized, right? So if magnesium is a better reducing agent, all the oxidation is going to again happen at the magnesium away from your big tank that you stored underneath the ground, because you probably don't want to have to go dig it up every week, right? As it starts to rust out. So that allows, again, it to sort of protect it. Titanium in ship's hulls are sometimes used for that. So this is the idea of that. Again, magnesium is pretty much where all the oxidation is going to occur. This guy would then become more like the cathode in this reaction, again, thus sort of protecting the tank. So again, you don't have to maybe dig up the ground as much. Any questions on corrosion? So you just need to know what corrosion is, a couple ways to prevent it. Let's talk a little bit about here to finish this chapter. We're going to talk about electrolysis, and electrolysis is the process in which basically electrical energy is used to create a non-spontaneous process to occur. You could do electrolysis, for example, water. You could run electrical current over water, and it will break water back down into its elements. And in a lot of cases, electrolysis will do that. It will take a substance and sort of return it back to its sort of elements, which, as we know, doesn't normally happen, right? Water doesn't just normally like go off into hydrogen and oxygen gas, but you can sort of force it to happen that way. Same thing if you took something like sodium chloride, it doesn't just normally go back to sodium metal and like chlorine gas. You can run an electrical current over it, and you can force it to sort of go back that way. Now, it is a little bit different than what happens when we make something like sodium chloride. So, for example, when we make something like sodium chloride, we have sodium metal plus some chlorine, right, gas. And that makes some sodium chloride in this case, right? And maybe do a little balancing. It feels like the right thing to do and all that good thing. So this is actually the making of sodium chloride, which is an ionic compound. If we look at the oxidation state of sodium, it is 0. Chlorine, it is 0. Here it is +1. And the chloride here is -1 when they do come together. So in this particular case, when we make sodium chloride, the one that's being oxidized is which one? It is the sodium, right? It's going from 0 to +1. It's being oxidized. And by default here, this guy is being reduced, which it is, going from 0 to -1. Now, if we started with sodium chloride and we wanted to basically go the opposite way, we're basically going from sodium chloride back to sodium and chlorine. That means we're actually starting with a +1 and a -1 here. This is going to be a 0 and a 0. In this particular case, the one that's being oxidized is which thing here? It is the chloride in this case. It's being oxidized. And it is the sodium ion that is being reduced. It is opposite in electrolysis. That's what you're basically doing electrolysis for, to force it to go the opposite way, because it doesn't normally do that, right? So that's why when we look at our electrolysis cell here, the half reaction that we see for this is actually the chloride ion losing some electrons. And on the reduction side of our electrolysis cell, again, is sort of the opposite of putting it together in a traditional, maybe galvanic cell. It is our sodium that's actually going to gain those electrons and be reduced back down, in this case, to liquid sodium. And in this case, obviously, we would form our chlorine gas. So sometimes people, a lot of times, will get sort of the half reactions backwards when you're kind of doing electrolysis, because it's kind of going the opposite direction of sort of how we normally think about it. And that's important, obviously, for calculations, or something that we would be doing next time, maybe, I think, is a good stopping place, I think.